Hi everyone, welcome to this session on exposed to risk. Our major intentions are using the observation or observed data to investigate the mortality. So basically, we're looking at the whole. Our intentions are to look at our investigation, like how many deaths or any other risk have occurred, and what is the period of observation during the period of a particular observation, like how many deaths have occurred in that particular uh, observation. And we're trying to look at the computation of the mortality rate. If it's in a discrete form, we compute the qx, or in the continuous form we have what the instantaneous rate of osmolality, which is nu(x). So that is the prime intention of this session. So before we get more and more into details on this particular session, the first important aspect is we look at the term called exposed risk. So here we're looking at two major dimensions. So one, we're calling it as central exposed. So here we're looking at what ex and c, and it's generally associated with the waiting time. This is actually observed, and when the death happens, it is only counted upon the period of time. So this is what we call the central exposed to risk, and it's applied in the multi-state. So it's applied in the multi-state model or the Poisson model. We're also supposed to design the initial exposed to risk. So here in the other side we have the initial exposed to risk. We are the initial exposed to risk, and we can try to bring the relationship either through approximation, which is say initial exposed to risk is equal to central exposed to risk plus half of the number of deaths that have occurred during that particular period, which is more like an actual estimate, which we talked about which we'll talk about later, which is in the binomial model. So that's why we use the initial exposed to risk. Now here we are more and more spending time in terms of understanding whatever the relation between the various forms of exposed to risk. So we will look at a few more aspects, more and more pertaining to exposed to risk. Now generally, whenever we are using the central exposed to risk, which is more like the total more observing waiting time, so we are primarily concerned about the time spent by each life during the investigation process. So it may not be an integer, it must be lesser than an integer, because I might not observe a life between x and x plus 1. So life could have left between that interval. And whenever we are working with initial exposed to risk, we have to make the adjustment that all the data that are occurring are uniformly distributed. And based on that assumption, we have derived that formula Ex is equal to Exc plus 1 over 2D. So even if I'm going with the multi-decrement table of the multiple decrement state, I can very well accommodate the central exposed to risk. But the initial exposed to risk cannot be used in the initial exposed to risk because it's used in the single decremental model. So from all these dimensions, it is very clearly understood that the central exposed to risk becomes a much more important factor compared to the initial exposed to risk, because the calculation wise central exposed to risk is coming directly from the data. We have observed n lives for a period of n1 periods, so the total period of observation is n1. During this period we have d deaths which have occurred. So I can very well talk about the central exposed risk as n1 for a period of indirectly. So it's a direct observation of the period of direct observation of life, and the total observation of lives is giving me the central exposed to risk, which is Exc. So when new lives have entered or some existing lives are censored, it hardly matters about the computation of the central exposed to risk. But if I'm dealing with the initial exposed to risk, we are making lots of adjustment, because even if the person has died between the observation, we are trying to calculate the initial exposed to risk and adding up the difference and the data and everything, and for each of every life to the central exposed to risk. So here we say initial exposed to risk is not a straightforward calculation, because I'm making adjustments to data and we're making some kind of assumptions to the distributions of the force of mortality, and based on that we're trying to do the computation of the initial exposed to risk. That is one of the primary reasons with the initial exposed to risk. So initial exposed to risk is slightly complicated to compute in comparison with the central exposed to risk. And one more important benefit of central exposed to risk, so one of the other benefits, so even if there are multiple decrements, not just the death, probably there are surrenders, probably there are some other reasons a particular life has left the observation. So all these things can quite be handled, because they can only be, because we're only considering a specific period of life. So if a particular life has left the observation because of any particular reason, we are counting that as part of the exposed to risk, central exposed to risk calculation. Whereas if there are multiple decrements, there is no way I can change the initial exposed to risk, or even if the increments, they could be handled with the central exposed to risk, but it is very difficult to handle with the initial exposed to risk. So because of all these reasons, we find a lot of reasons with difficulties with central exposed to risk with the initial exposed to risk, whereas the difficulties cannot be the case with the central exposed to risk. because are dealing with, we are dealing with more and more. So if we're dealing with more and more of multiple state setup, probably central exposed to risk, is effectiveness in the computation process. So that is one thing. We are narrowing down on a betterness association of the exposed to risk compared to the initial exposed to risk. Now, the second thing we are more interested in looking at is the concept of homogeneity of the various risk classes. Because whenever we define homogeneity with respect to a group or a setup, like many of or almost of all the members or the lives in that particular group have the same characteristics or similar kind of characteristics, or they follow a similar stochastic model of mortality. That is what we mean by having a more homogeneity. So the characteristics for the groups, for the entire group, is more or less similar. That is what we are calling as homogeneous. Even if we have a broad group of lives, it is very much essential that I differentiate those lives into a homogeneous group. It is a very essential aspect where I subdivide the groups or the whole data into homogeneous groups, especially when I have to go with mortality investigation. So it could be a grouping based on age, gender, type of policy, or a grouping based on smoking status. You can think of so many criteria, or duration of the policy, how long, or the age of policy. The age of the policy, we can think of the age of the policy, how long the policy is in force, or you can look at the size, like the sum assured associated with the policy. So policies similar levels sum assured can be grouped together, or you can look at some grouping like occupation level of or insured, or impairments based classification. On some grounds, we are looking at classifying the overall set of lives. That is why we are bringing more and more of homogeneity as part of the analysis. And the reason why we really get into this kind of understanding is any group of lives we are looking at, for that group, based on the characteristics of the group, we can create an appropriate model, the base intention. So the base intention is to create an appropriate model. We have seen in the case of like a group of data, we're not creating a model on the basis of one observation. Based on a homogeneous group of observations, we have created the models accordingly. So from that dimension, we see having a homogeneity in a group structure will help us derive a mortality rate appropriately to a different group. I've seen in the proportion hazard model, we were able to compare the hazard rates for one group of characteristics to the other group, or how one characteristic had an impact, had a impact on the hazard rate when the others were constant. So this kind of grouping and this kind of estimation becomes more and more easier if the group are subdivided on homogeneity. But again, having again too many groups is still a problem. We may not have sufficient data to really do the observation to come out with the model. So too many, too less will be a less. Too less is a problem. So that's why the optimums of groups need to be understood. So otherwise, what could have really else happened if I'm not able to build an homogeneity in the group? The mortality rate that is coming out to basically use for the data to be to the determination of premium. So it could be either overestimated or underestimated. So because of that, we may so charge a higher premium. You can charge a higher premium for a certain number of people, or we could charge under premium, and here we charge lesser premium, which is in respect to the risk. So that is where we need to make sure that the homogeneity we're bringing the group should be grouped in such a way that all the risks that are falling in that particular group are large extent they are appropriately having the similar risk characteristics, so that the premiums which are charged are not too high or even too low. So excessive subdividing of the data, we are more and more breaking down the data into exact homogeneity, exact subgroups. So we're going to have less number of groups. Okay, so here we've looked at the premiums, and probably the sample size that we get in each of the subgroups will actually go down. So as the sample size reduces, we know that whatever the estimation we're coming to, we're going to come out with, it will have large amounts of sampling errors. So having those kind of stuff will create more and more problems with respect to estimating the mortality data, and in respect to mortality rate estimation. So from that dimension, it is very much necessary that we don't subdivide the data into too many groups. And we have seen that we can subdivide the data into many factors like age, gender, smoking status, how long the policy has enforced, the types of policies, the size of the policy, occupation. On all these grounds, I can very well subdivide the entire population and try to come out with the rate mechanism for each group separately. But the whole grade of mortality estimation goes with one major concept. So our next concept is the principle of correspondence. So look at the principle of correspondence. So what does this principle state? It clearly states that a life, so as a definition, I'm looking at a life that is alive at time t. So if I have to include this life into exposure, so it has been included into exposure for age x at this time t, under the assumption that if this particular life dies immediately, if this life dies immediately, the same life will be counted even for the death related data. In a simple way, there should be a kind of synchronization between lives of which are included in the exposed to risk at the death. So I cannot use a different age convention, or I cannot use the age notation. The age notation for the death should be similar to the one I'm using for the exposed to risk. I cannot have a exposed to risk calculation having, let's say, year last birthday, and I cannot have the number of deaths for age X classified as age near his birthday. Both of them should follow the same kind of notation. That is what is being coming out of simple principle of correspondence, and that is majorly applied only to central exposed to risk. So this principle comes only to picture with only the central exposed to risk. Now, whenever we are looking at the calculations relating to the central exposed to risk, this is where the crux of this chapter is. What is the calculation? What is the calculation that is going on with respect to central exposed risk? Now what we're saying is we're taking 2 days, and I'm interested in the difference of 2 dates. What are these difference of 2 days? So one, we're talking of the entry point. So when I'm looking at the entry point for a particular age, I'm looking at 3 things. So I'm looking at 3 things here. So I'm looking at the date of birth, or date of start of age X, one thing. So here maybe I'm looking at the date of start of age X, and the next thing is date of start of investigation. Investigation or observation, and date of entry into investigation. So which of 3? Which is the latest of the 3? So this is what I call the latest of the age X. Similarly, when I'm looking at exit point, again I'm looking at date of end of age X. So here I'm looking at date of end of age X, or date of completion of investigation, or date of exit. Of which of these 3, which of this is the earliest? Now I'm computing the difference between these 2, which is the earliest, and the latest. So the difference between these 2 is the contribution. This is a contribution to the central, is a contribution to EX. So this is how you calculate the contribution to central exposed to risk. So the requirement is coming out as the difference between the exit point and the entry point. So even if the entry point is 0, we can take the contribution to the central exposed to risk for the edge x directly as 0 itself. So that is the way we go ahead with terms of computing the central exposed to risk, right? It is purely, I'm looking at the dates, and based on the dates I'm trying to compute the contribution to the central exposed to risk. It's a straightforward mechanism. Once we remember this kind of rule, it is very easy to go forward with almost every calculation. In respect of what is mechanism, that is me used to compute the date of birth or compute the age, given even if I'm going with the age last birthday or next birthday, whatever it is, what is the date on which the age x is going to start. So based on this, I can decide on the entry point, and that is one which I can use to determine the exit point, and which can help me in terms of computation of the central exposed to risk, right? So looking at the other dimensions now, the census approximation mechanism. Even though individual data is given, so we're looking at the census approximation mechanism for computing exposed to risk. So now we look at the investigation start at a particular point, and it has ended at a particular point, and we are looking at the age x, people with age x at a particular point t. So this is somewhere here t, we are t, we are talking at people whose ages x at this point t, and we're denoting that this is a population. Now all we are saying is if this vacation has started here and it has ended at time period n, all we are saying is the overall contribution of the central exposed to risk is nothing but the integration of the entire time period, the population x at each of the points, the population at each of the points which are observed during this entire period. I'm integrating across 0 to n the population at each of these points, right? Probably at exactly time period t, I have observed px of t kind of lives, and p plus 1 I've observed observation on t plus 1. So the central exposed to risk the entire period I can say is the integration from 0 to n px of t. And if at all I don't know the pattern with respect to the px of t, we are going to simply use the trapezoid rule to estimate the average value of px of t. So all we are saying, we're dividing it into small intervals. I'm saying half px of 0 plus px of 1. So I'm looking at the time period of 0 and a time period of 1 at the how many people have with the age of x. So you take the average of these two, and similarly the age of these two, and you take the averages of O and the px of 1 plus px of 2. So keep doing this kind of process up to n period, px of what is the overall average population of a particular period. So that is why we are using this kind of trapezoid rule to typically approximate the center exposed to risk during this entire process, right? Because we need it from point 0 to point n, what is the overall population that is exposed to risk during this entire process. And because we cannot know the equation that is associated, or the function that is associated with the population, we are using the numerical, which is the trapezoidal rule, to estimate the center exposed to risk, right? So that is one more thing we're looking at. And here the calculation associated with this approximation part becomes the most important aspect in this aspect of calculation. We are looking at the understanding of the rate interval. To what interval is it applicable? So whenever we're using at the rate interval, we're talking about 1 year period from the age x to x plus 1. During this period, the age is going to be x itself. So from 1 year, which is the start of the age, to the end of attaining the age x, for every individual life, we are calling it as rate interval. So it's just the period in which it is just the interval in which the age is going to remain constant. So even if using the age next birthday, when we are talking about age next birthday, which is being used for classification of death, so if I'm saying 40 next birthday, the current birthday is 39. So if I'm using that the death, if the person has died at 40 next birth, then currently is at 39. So it could be at 39 one day to 39 364 days, 365 days. So the rate interval that we're applying here is x minus 1. The current age is anywhere between x minus 1 to x. So that is the reason when the rate interval that is applicable for this definition is x minus 1, right? And similarly, if I'm talking about age x nearest birthday, then the rate interval is becoming x minus 1 over 2, because if I'm saying this age is 40, then his age could be between 39 and a half to 40 and a half. So the age where his age is going to be constant is in the x minus 1 interval. Okay, so if I'm looking at x minus half, it is the rate interval that is applicable for that interval scenario. And here we are trying to calculate the mortality rate. Once I have the investigation process in place, and I also have the number of deaths that I've observed during that observation process, either I can use if I have to estimate qx, which is a discrete mortality rate, then I can look at the actual number of deaths, then I divide by the initial exposed to risk, and this is simply estimated as qx plus f. F is the age at which the start is the age at the start of the interval. So this is one way I can use the Q-type mortality by using the initial exposed to risk, but default, or if I'm using the force of mortality mu x, then I'll go it with dx divided by center exposed to risk. And here I'm looking at the mu type estimate x plus f plus 1 by 2, because here we are assuming that the deaths are whatever they recorded as happening at that moment of that time are uniformly distributed across the entire interval. That's the reason the estimate is coming out as mu x plus half plus f, which is associated with the rate interval, which is associated with the x plus half. So these are some of the things you need to take into consideration, and one is the most important information associated with the census formula for computing the center exposed to risk, and using that particular concept for computing the center exposed to risk, we can very well compute and derive the death mortality for the various observations, as well for the various homogeneous groups. A few remarks regarding the same have been worked out in the book. So we'll come to the end of this session. Thank you so much for attending it and being participant. Uh, I'll see you in the next session. God bless.